All right, so this is May June 2022 paper 1-2, and a reasonable estimate he asks you. So it says 1 gram is the mass of a grain of sand. Now this estimate is too high. 1 meter cube approximately, or 0.01, yes, meter cube volume of a tennis ball. Again, this is an estimate is too high. You can do this by visualization, at least, that a tennis ball probably has a diameter of, let's say, 15 centimeters. You can use this 4/3 pi r cube and see that this is not going to be 0.01 meter cube. This is 1 joule to lift an apple from feet to waist height, for example. Now, apples are usually 50 grams approximately. Now, 10,000 watts for a light bulb. This is too high again. The closest possible is option C. What is the symbol for SI based on temperature? Now, this is tricky. You see, this is straightforward, which is Kelvin, but you might ignore this option at the very first glance. Why? Because capital K is for Kelvin and small k is for the prefix kilo. Many students, and I've known many people as well who don't know this distinction. Question number 3. What statement about systematic error is not correct? Systematic error is due to the system. This is a constant sign problem. If you're constantly overestimating, then that would be a constant sign problem. You're doing the same mistake again and again, and it can be corrected if you once identify what the problem is. Okay, so he says is not correct. So systematic incorrectly calibrated. Yes, incorrect calibration, 0 error, incorrect position of the person, or some environmental factor that is constantly creating that problem. One particular type system can affect the measurements by same. Yes, this is one of those things that we talked about. That is a constant sign. For example, if you're measuring a volume, which you know that a true value is 15, and it is constantly giving you 17, or 2 more than the actual value. So this is a constant overestimation of +2, for the sake of example, right? So this is also a systematic error. Then we move towards 0 error. 0 error is a classical example of systematic error. So option C seems to be the correct answer by elimination, but let's discuss this. Effect of systematic error can be, no. By repeating and taking average, random errors can be reduced. But for systematic errors, you have to identify where the problem lies. And if you identify where the problem is, if you correct it, the error is gone completely. Random errors can be minimized by taking repeated readings and taking average. Question number 4 is tricky in terms of words only. Otherwise, this question is very simple, straightforward. He says, this is the final velocity, this is the initial velocity. He says the change in velocity. So change in velocity is final velocity, which is this, minus the initial velocity, which is u. Now, this is a simple vectors problem. You see, if I have u in the right side, if I make minus u, then I will have to make it in the opposite direction. This is how vectors are represented mathematically. That sign represents direction. So if I were to find out this scenario, v minus u, then u would be actually in this direction. And if that is the case, then the resultant, very plain and simple, looks like this, which is going to be option B. Again, I remind you, this is the trick word, is going to get you confused about the question. No need to worry. And some students generally, looking just at this direction and this direction given in this situation, mark the resultant like this, and A seems to be the most quick but wrong answer. Question 5 is pretty straightforward in terms of distance displacement. He says this is the radius, this is the circular track. Okay, fine, we understand this. The car takes 4 seconds to move from P to Q. So according to the full circle, let's say, it takes 4 seconds to come here. It says what's the average velocity. Now, velocity is simply displacement over time. We know that the time it takes for this system or for this situation to take place is actually 4 seconds. But what is the displacement? So displacement will be the distance between the starting point and the ending point, which seems to be very simply calculated, or can be calculated as Pythagoras theorem. So displacement of P to Q is under root 12 square plus 12 square, right? So if you do that, your answer comes out as, let me just try this. So 12 square plus 12 square is 288, and if you take the under root of that answer, that is going to come out as 16.97. So this is 16.97 meters displacement in this direction. So 16.97 divided by 4 gives you an answer of 4.24. So this is 4.24 meters per second, which is going to be option A. Question number 6 requires a bit of diagram and understanding. He says that water surface deep well is 78 meters below. Okay, right. The person at the top of the building or the cliff probably throws a heavy stone down at the well. Air resistance negligible. The speed of sound is 330 meters per second. What is the time interval between the person dropping the stone and hitting it hit the water? First, we need to understand what will be the time taken for the ball to fall from such a height, or the stone to fall at this water level. Let's say this is the water level. So he is throwing it with the initial velocity as 0, and this is 78 meters below. So we can use the equation to find the time very simply. S equals to ut plus half at square. This becomes 0 because the initial velocity was 0. This is 78 equals to 1 over 2 into 9.81 into t square. Don't forget to take the under root, and the t will be 3.98 seconds. So it takes 3.98 seconds to come down, and when it does encounter water and creates a splash, for example, it creates a splash, sound wave will start following or start moving in the upwards direction so that the person can hear that the stone has actually hit the water. So how much time is that going to take? So that will be simply speed equals to distance over time. The distance sound has to travel in the upward direction is 78 meters. Time taken, we don't know, but the speed of sound is given in the question as 330. So 330 gets replaced with this position. So time comes out as 0.236 seconds. So the total time of the journey from throwing the stone downwards until you hear the sound upwards will be 3.98 plus 0.23. So the total time of the system is 0.236 plus 3.98 gives me 4.22 seconds as my answer, which is going to be option D. Question number 7, he says, which statement is not the requirement of a pair of forces to obey Newton's third law? Forces act in the opposite directions. Yes, they do. For example, if there is an object A, there is an object B. Object A attracts B and object B attracts A. They are in the opposite direction. They act on different. Yes, this is one of the conditions. They act during the forces act on objects when in contact. This is not necessarily required. The forces are of equal magnitude. Yes. Now let's look at a situation where this option does not happen. The contact is not necessary. What about the Earth's gravitational pull on the moon and the moon pulling the Earth? Are they in contact? No. What about the sun pulling the Earth and the moon at the same time? Are they in contact? No. What about two magnets trying to pull each other towards itself? Are they in contact? No, not necessarily. So being in contact is not a requirement for Newton's third law to actually show its position. Now question number 8 takes a bit of time, and it takes a bit of, it's very difficult to understand. It's very difficult to at least accept that what's happening in the question. Let's break it down and let's bear with me with the question. I will use another example that is already a part of O levels and A levels to just give you a hint how to visualize this. Now, he says that the mass of the sledge is approximately 40 kilograms and the mass of the child is 20 kilograms. And the child is pulling the rope with a force of 12 newtons. Now, when this loops over this pole, I observe that this will be a force of 12 newtons in the right side direction. Okay, now let's isolate the child and the sledge and this 12 Newton force. Let's see what's actually happening. So let me draw that case over here. So this is our sledge, for example. This is where the boy is standing. This is where the child is standing, right? And I realize that the sledge is experiencing a force of 12 newtons in this direction. Now, we understand that there needs to be a friction between the feet of the boy and the sledge on which it is standing. If there was no friction, then the sledge would slip right under its feet and he wouldn't even know what hit him, right? But we do understand that this is frictionless. The floor is frictionless, so there is no involvement of friction from that part. So the friction should exist. Let's look at it from this perspective. Friction should exist so that the boy can move along with the sledge. If both objects start moving, they should be moving in the same direction, right? Now, what's happening at this point? What is the direction of the friction in this case? You see, to explain this, let's understand how we walk. You see, if let's say this is our foot, right, in the walking position, you push the ground backwards, and the ground applies an equal and opposite reaction force in the opposite direction so that you can move forward. That is how you are propelled forwards when you are walking. Same thing happens with the car tire. If the car is moving in this direction, the tire has to rotate in this direction. So the tire is pushing the ground or the road backwards, and the road pushes the tire and the car forward, right? Something similar, but in the opposite direction is going to happen here. So what's happening over here is that friction is acting in the backwards direction, trying to hold back the child in its ground with the floor, with the sledge. But the sledge will provide a forward force or the forward reaction force in terms of friction so that the boy can move along it, or the boy can move with the sledge, right? So again, let's look at it again. There needs to be a friction experienced by the boy to move along the sledge so that they can move in the same direction. Now, if this friction exists and the sledge is applying, or you can say the sledge is providing this friction, then of course the boy will also experience a friction in the backward direction, primarily based on this Newton's third law idea. Simple as that. So from the child's perspective, we'll have two equations for this. From the child's perspective, we have F equals to ma, and from the sledge perspective, we also have F equals to ma. Now, from the child's perspective, I see that there is a forward force of 12 newtons trying to pull me forward, but there is a friction force in the backward direction which is going to oppose the motion that I'm going to experience. So 12 minus F equals to my mass, or the mass of the child, into acceleration. Okay, fine. Equals to, from the sledge's perspective, I realize that the 12 Newton is in the right direction, and the friction provided by the sledge to the child is also in the same direction, the forward direction. So both acting in the same direction. So 12 plus F equals to mass of the sledge, which is 40, into acceleration, which is going to be same for both of them. Now I understand that the acceleration of both objects should be same, so we can make this subject the subject of the formula. You can realize this very conveniently, that this is going to go towards that side. And once you equate both of the sides, for example, once you equate both of them, you will get, first you will find the value of acceleration, right? Or what you can do is simply divide this whole system with 2. So this becomes 6 plus 0.5 F equals to 20A. I've done this so that both sides become equal. So this is 20A and this is 20A. So now I can conveniently equate them both. That's just a mathematical technique, not physics. Okay. So this becomes 12 minus F equals to 6 plus 0.5 F. When you are done with the algebraic manipulation, you will end up with an answer of 4 newtons. So this is actually answer of 4 newtons. Okay. I hope that we understand this question. Okay, so question number 9, again a repeated question. He says that we have a stone S and a rubber foam ball R, identical spheres, which means that their sizes are same. This is S and this is rubber R. This will be heavy and this will be lighter. And if they are thrown in the presence of air resistance, of course, if they reach terminal velocity, then air resistance is present. Which graph shows them shows the behavior? You see, both of them are going to experience the initial acceleration to be 9.81. In fact, they are both going to experience it throughout their life if air resistance was absent. But if the air resistance is present, now the air resistance is going to act on the object. And we know that as the speed increases, the drag and the air resistance also increases. But it's going to affect both of them differently. The heavier object, although has the same surface area as the lighter object, should experience the drag in the same way. But since it's heavy, it can pierce through air much more violently as compared to a lighter object. So it will take some time to reach the terminal velocity. So it will stay in acceleration for a longer time. So its speed should be higher than R at least. And R, since it's lighter, it cannot pierce through the air resistance as much as S, the heavier stone. So it will encounter terminal velocity, or it will face terminal velocity much earlier on, because its drag will become equal to its weight. Because to become equal to the weight is an easier job. You see, in both examples, let me make this over here. So this is the stone S, and this is the object R. Let's say this is 200 newtons, and let's say this is just 50 newtons of weight, of course. And they both have to experience the drag. Okay. Now, of course, since the surface area is exactly the same, they're going to experience the drag in the same manner, but the equation is going to become F equals to ma. So what does that become? Weight minus drag equals to ma. If the acceleration has to become 0, because we want to attain terminal velocity, then this equation actually comes down to 200 minus drag equals to ma. And for this one, it becomes 50 minus drag equals to ma, right? Now, to become equal to 200, drag has to prolong its effect. It has to act for a very, very long time, because it's going to start from 0 and get to 200. Until it doesn't get to 200, the acceleration does not become 0. So to get to 200, it will take some time. To get to 50, it's going to take less time. It's going to happen much quickly, because it's a smaller force to counteract by drag. That's why, since it is going to hold out for a longer time, its acceleration will slow down at a much slower rate. The object will attain a higher speed as compared to R, but eventually reach terminal velocity one way or the other. So S will have a higher speed, R will have a lower speed, and they both will reach terminal velocity eventually, because it's mentioned in the question. I hope we understand what's the problem in terms of mathematics of this. Why S takes longer and can travel at a higher speed. Question number 10 is nice in terms of at least relative speed rule. So we have a perfectly elastic head-on collision. If it's perfectly elastic, then the relative speed rule applies. So what's the initial situation? So he says that they're both moving towards each other, right? And he says that, all right, they're perfectly elastic, and Y moves towards the right side with the speed of 7 meters per second. Okay, fine. So what's the relative speed before the collision? Since they're both moving in the opposite direction, I'll have to add their speeds simply. So 15 plus 5 becomes 20. Okay, fine. So now they're moving, now it is moving towards the right side with 7. So relative speed after has a contender, or has a value of 7. I want to make this 20. So what should I do with the 7 so that it becomes 20? Because I know that relative speed before and after collision should remain same if it is supposed to be a perfectly elastic collision. So what should I do? What can I do with 7? Should I add something? Should I subtract something? What can I do with 7? So I can see that the option that I'm given with is 3 and 3. So 3 can't be the option, because even if I add 3 or even if I subtract 3, there is no way in hell I'm going to reach 20. There's not a chance. But let's try 13. I want to add 13 into this so that it becomes 20. How can I do that? Let's try both options. So Y is moving towards right side, and X is moving towards the left side with 13. Yes, they're moving in the opposite direction. I will add them together, and yes, this is my answer, becoming 20. But let's, for the interest of science, try option D. So it says option D towards the right side. Option the sphere Y is also moved to the right side. Since they're moving in the same direction, I'll have to just simply subtract their answer. So 13 minus 7 gives me 6. Yep. So is that equal to 20, the relative speed before the collision? No, it's not. So this is not my answer. It would have been B. Question number 11. What forms the torque couple? What describes the two forces? Since he's only asking about forces, I'm only going to think about the forces. They're in the same direction? No, they're supposed to be in the opposite direction. They're perpendicular to each other? Not necessarily. One force is over here, one force, no, this is wrong. They have the same magnitude. Yes, this seems like the best option. They pass to the same point. No, necessarily they don't have to do that. If they pass to the same point, for example, if this is this and this is this, if they're passing from the same point, that is not going to become torque, or that's not going to become a couple, for example, at least. Or even if it was like this, if they're passing to the same point, this is going to become something else. So it's against the definition of torque at least, or couple at least. So this is an interesting question in terms of repetition. He says that the system is in equilibrium. Okay, good, nice. So there is going to be a component of tension over here. There is going to be a component of weight of the rod over here. And then he says that there is a force on the rod at the hinge. So according to simple coplanar forces, whenever we say coplanar forces, if the system is in equilibrium, they will find a point of intersection at a common point. So what is the point of intersection? If I extend this tension, like, sorry, let me draw this again in a better way. If I draw, if I extend this tension like this, just use a ruler and a pencil and draw this on your page if you're doing this on a printed paper, and then extend this weight, for example, like this. Now these two forces are going to find a common point of intersection at this point. Now if this is in equilibrium, there should exist a force that is going to pass through this point at any angle. We don't care. It could be passing from this point, could be passing from this point, could be passing from this point. But luckily, we understand where this force is coming from. You see, the component of tension that is responsible for acting against the weight is going to be in this direction, right? And there is going to be a component of, this will be, let's say if this is theta, this will be T sine theta. And there will be a component in this direction, which will be called T cos theta. This component, when reaches this point, is acting on the wall, and the wall is applying an equal and opposite reaction, which is the normal reaction by the hinge, at least at this point. So what does the normal reaction become equal to? This is equal to T cos of theta. And if this rod was allowed to move, where is it going to go? This will slide down. Or you can say it is trying to slide down, but it is being held back in this position by a frictional force which is in this direction. Why in this direction? Because this rod is trying to go down. If it was allowed to move, it is trying to slip. It would have wanted to slip at this point. So the friction is going to oppose the motion of this object wherever it tries to go, or wherever it is trying to go. So the resultant of these two vectors is going to be in this direction. Now if I extend this vector, it passes through that common point. So the force, direction of force resulting in the vector representing the hinge force is actually D. All right, question number 13 is from Moment and Hooke's law, employing both concepts at the same time. We know the mass of the child, we know how far away it is from the pivot, from the hinge. He is going to ask us what is the compression. So simply the clockwise force produced by the boy is going to be used to compress the spring, and the spring is going to try to hold him back. So the spring is trying to stop this from coming down, of course, right? So the moment generated by the boy is going to be equal to the moment, or at least the force created by the spring. So this is a moments problem. So clockwise is going to be equal to anti-clockwise. So simply take the moment of the boy, which is 40 into 9.81, make it the weight of the object multiplied by its distance from the pivot. Be careful about this. Its distance from the pivot is actually 5, which is being compensated or being held back by the spring by a force F, which we don't know right now. And the spring constant is known as 10 kilonewtons. We'll get to that later. And then we have a distance, which we already know, which is from the pivot, it's 2. Now, when you do that, you find the force to be equal to 981 newtons. So the spring is experiencing a force of 981 newtons, and it is applying a force of 981 newtons to hold back this child at this position. Then I use F equals to Kx. This is 981 equals spring constant at 10,000 kilonewtons per meter into X. X comes out as 9.81 centimeters. Of course, you'll have to convert this Newton per meter into meters. First, we find meters, and then we convert this into centimeters. So this will be option C. Moving to question number 14. This is a trick question. It's going to be solved very quickly. A granite rock of density rho is at Earth, transported surface of another planet. Let's say we go to the moon, or let's say Mars or something else. The gravitational attraction is twice as much as the Earth. Does it matter to the density? No, it does not. Why? Because density is equal to mass over volume. Whatever rock you were taking to any other planet, has its mass changed? The mass is the number of atoms or the number of dust particles, the number of small, tiny, itsy-bitsy molecules inside this object. They are still the same. The number of atoms, let this be 1 billion. They're still the same. And they're still occupying the same space. Be that on this planet, be that on any other planet. They're still occupying the same space. So the density, no matter calculated on Earth, no matter calculated on the other planet, it's going to be the same. It wouldn't change. Because if you want to measure the mass, you will most likely be using the beam balance. And we know that beam balance actually nullifies the involvement of gravitational attraction. It tells you the correct mass irrespective of the planet. So this was a trick question. The density will not change. It's going to be B. Question number 15 is a good question. It revises the concept of pressure and gas pressure. It says that the system is in equilibrium. I believe so. Yes, stationary liquid, that means the system is in equilibrium. So now we're going to decide which liquid is trying to go where and which pressure is trying to do what. You see, if you look at this difference of height, first, very quickly identify the difference of height. What is this? You see, this liquid is present over here. Let's break it at the center, and this liquid is present over here. If there was no gas pressure, if there was no open container, if there was nothing of the sort, what would happen to this liquid? This extra liquid will fall down and this level will rise up until both of them become equal, right? I hope that we can understand this visualization. So on the left hand side, I see this is the liquid. On the right hand side, I see this is the liquid. They are both trying to come down, or they're both trying to exert the pressure in the same direction. So since they're exactly the same for both columns, they don't participate in this system. They're not participating in the systems or creating any pressure because they're exactly the same on both sides. Now I realize that the two sources of pressure that are acting at the center point are this liquid height and the gas pressure P. So I can see that the pressure, total contribution of pressure from this side on the liquid is actually the rho GH of the liquid, rho GH plus P2 pressure of the gas held inside this space. Now what is this H? This H is actually the difference of Y and Z. Okay, so I will write down rho G into, let me change the variable. This will be Y minus Z equals to, not equals to, but plus P2. And this is being held back by just one element of pressure, which is on this side. So P1 is holding back. There is only one pressure on this side. So P1 is holding back two elements because the system is in equilibrium. It means left hand side is equal to right hand side. So it is holding back both of them. So P1 should be equal to both of them. Okay, fine. If I rearrange the equation, I can see that P1 minus P2 by bringing it over there is going to be rho G into Y minus Z. So the most likely option that actually matches this description is C. Question number 16, he says what's equal to power? So power is equal to force into velocity is a very common formula. Straightforward. Question number 17, this is a bit tricky, but only in terms of maths, so no need to worry about it. He says that we have two systems, okay? The first system says that it's 40% efficient and the second is 5% efficient. He says that they have same useful output. This is where we are going to draw the line or the common point for both systems. This is where they're common. Let's see what that means. You see, if I look at the new system, let's say, which has, let's say, PO as its output, and I look at the old system, which will still have same output as P0 because they're saying same useful output, which means that if this is producing 200 joules, then this is also producing 200 joules. We don't care what they demand from the input. All we care about right now is this piece of information that they're both producing same outputs. We don't care, right? Okay, so this, let's say, is 5% efficient and this is 40% efficient. Now we want to calculate the useful input, the total input power. So I want to go back to the input power and looking at the formula for efficiency, that is useful output divided by total input multiplied by 100, right? So if I want to find out the total input and this is equal to the output power, for example, or at least the efficiency, right, which is given to me of the systems, then I can replace them in their respective positions to find out the input power. So according to my understanding, the shortcut would be that this will be actually P0 divided by 0.4. Okay, if I divide, let's say, this 200 joules as given in the previous example with a 0.4, I will get how much energy is going to be provided into the system, of which 40% will be 200 or will become 200. Similarly, over here, I realized that P0 should be divided by 0.05 to calculate its input power. And it's very plausible. This is going to be very high answer because we have to provide much more energy, because it's only 5% efficient, is only converting 5% of what I'm giving to it into something useful that I actually want. So since I'm going to do a comparison, so this will be new lamp, which is P0 divided by 0.4 divided by P0 divided by 0.05. Now this is plain and simple algebra. Please use your calculators. So you can simply write this down as 1 divided by 0.4, use the fraction sign, 1 divided by 0.05. You will find that your answer comes out as 0.13. Please, this is just a calculator problem. Question number 18 was is actually from kinematics. He says, what is going to derive the formula for kinetic energy, or what is useful, what's not useful? You see, when you are trying to derive the formula for kinetic energy, this is where you start from. This is exactly the place where you start from. And to find the acceleration, to just simply find the acceleration, you need this formula, F equals to ma. Now, since you involve F, you are dealing with kinetic energy, you have to involve the work done as well. So work done by moving or while moving the object is also involved one way or the other into the system, or into this equation at least. Where this equation is given to you as Fs is basically the formula for the strain energy of the spring, half Fx. So don't be fooled by this. This is what is not required and will not be a part of the steps going from this to this, or at least from this to half mv square. Question number 19, simply replacing values. He says Hooke's law means no deformation. Young's model is given to you. The wire has a length of 1.6 and has a diameter of 0.8, which will be divided by 2. Spring constant is asked of the wire. So, okay, let's look at the question. So this will be Young's modulus equals to FL over AE. Okay. Now, if I look at the force constant, which is F equals to KE, I can replace KE in this formula. By the way, this formula is actually a shorthand of Young's modulus, which is stress over strain. So that becomes force over area divided by extension over length. You can simplify this to look like this. Okay. All right. So what to do next? So this formula becomes Y is equal to K times E into L divided by AE. E cancels out and you're left with KL divided by A. Since we want to find the spring constant, I'm going to take the rest of the elements to the other side. So A goes to this side and L gets into the division. So what do I get? K equals to, the formula becomes Young's modulus multiplied by cross-sectional area divided by the length. Let's replace the values, which is 2 into 10 raised to the power 11. Cross-sectional area will be pi r square. The diameter is given to us, which is 0.48 into 10 raised to the power minus 2. Divided by 2 whole square divided by length, which is 1.6 given to us over here. So K comes out as 2.26 into 10 raised to the power 4. Yeah, so that is going to be option B. Yes. Question number 22. Question number 20. A wire stretched by tensile force. Tensile force means it's a pulling force. Must be true. Okay, so what is the elastic limit, by the way? So elastic limit is something like this. First, you encounter the limit of proportionality. What is that? That's a mathematical problem, right? Because after this region, you cannot obey Hooke's law anymore. You cannot use F equals to Kx anymore because it's not a straight line. Simple as that. This is no longer y is equal to mx plus c. It does not do that anymore. So from that point where it fails or where it stops to follow mathematics is the point of limit of proportionality. Now beyond this point, we sometimes encounter a point that is known as the elastic limit. Now this limit or this region is where you don't follow Hooke's law, but after very small amount of force or extension, there is a small region which does not obey Hooke's law. But if you keep on increasing force to go to this point and you remove the force, it will come back to its original position without going plastic deformation, without going permanent deformation. This is that point beyond which if you go, it will undergo plastic deformation, and if you stay behind it, you will not undergo plastic deformation or permanent deformation. But this region does not obey Hooke's law, right? So he says what must be correct. So he says that the deformation plastic after, yes, it is plastic after that elastic limit. So this is the correct answer. Plastic until that, no. Deformation is always elastic until you breach elastic limit. Extension proportional tensile force after the, no. it becomes a curved line. This is what I've been discussing right now. It becomes a curved line between the elastic limit and the limit of proportionality. It's a curved line. It's mathematically not proportional. The extension of proportional is tensor for until there's a no. Again, wrong. 21. Which statement is correct for all types of progressive waves? So progressive waves always transfer energy from one point to another. They consist of vibrating atoms. It's for both of them. It's for all of them. They can be damaged. Yes, they can be. The distance from peak to peak and is equal to the wavelength. Yes, they all have that. But in terms of longitudinal waves or sound waves, it's from rarefaction to rarefaction, compression to compression. So this option does not apply to them. Sound waves cannot be demonstrated in ripple time, but it's a progressive wave. It carries energy from one point to another. When I'm speaking, or when anyone is speaking, the air particles are carrying energy. They consist of vibrating atoms. Vibration or vibration is a word dedicated for to and fro motion, forward and backward, limited space. Okay, so that's that. Okay, question number 22 is slightly tricky, but it's a good question to visualize how waves go about. Okay, so if this one direction is 0.7, then this complete would have been 1.4 meters, 2 times of 0.7, okay? So it says at one instant, the ball is at the peak of the position that is shown to you. Okay, fine, we don't care. The wave has a frequency of 0.2 hertz, amplitude of 0.7. The distance between the troughs and the distant peak is 2.4. So this is probably, this is lambda by 2, half a wavelength, right? So he says, what is the distance traveled by the wave in 20 seconds? Now, to understand 20 seconds, first we need to find out the frequency, right? So first we find out, first we find out the distance traveled. Do you see? The wave is moving in this direction. So the next phase of the wave is going to go like this. The ball is going to go down and it's going to go up, right? In the next phase of its life. So first, let's apply V equals to F lambda, right? First, let's find out the velocity. So the frequency is given to us as 0.2. What's the wavelength? It is going to be double of 2.4, which is going to become 4.8. So find the velocity of the wave. That comes out as 0.96 meters per second. And I have a time of 20 seconds. So let's multiply this with 20. I get a total distance traveled in this direction as 9.2 meters. So it means that from this point onwards, the ball is going to experience a wave that is going to move 19.2 meters in this direction. So how many times is it going to go down, up, down, up? How many times is this going to do that? And if it does, then what's going to be the distance? Okay. Now, I know the wavelength is actually 4.8. So what I want to count is, if this is 9.2, then how many wavelengths of 4.8 meters will actually make the distance 19.2 meters. Do you understand this point, right? So let's find out how many wavelengths do I need to do this. So 19.2 is my total distance. How many wavelengths are needed? So 19.2 divided by 4.8. The answer that I'm going to get over here is 4 wavelengths. This is 4 lambdas. So 19.2 divided by 4.8. You can check this, you'll get 4. So it means that there are going to be 4 wavelengths established after this happens. So let's make those 4 wavelengths. 1, 2, 3, and then 4. So how many times is it going to go up and down? So when it goes through one wave, it has to go 1 and 2, 1 and 2, 1 and 2, 1 and 2. So then it comes back to the same position. Okay. So 2 times, 2 times, 2 times, and 2 times. So one time the total displacement is 1.4. To come down, to go up, it's 1.4. So this is actually 2.8. This is 2.8. This is 2.8. This is 2.8. When you add all of them together, 2.8 and all of them, this is going to become 11.2 meters. So the ball would have traveled 11.2 meters while going up, down, up, down, up, down, again and again for 4 wavelengths. So this is going to be 11.2. Question number 23, repeated question for sound waves. He says, where is the pressure the lowest? Okay, so displacement is towards the right side. And if we look at the displacement, or in terms of their life cycle, let's draw the life cycle of each particle. So this is where they were originally. when there was no sound. Okay. When there is a sound, that means that they're going to move. So A has a positive displacement, it moves to the right to the new location. And B has no displacement, it stays where it is. C has a negative displacement, it moves towards the left, towards the new position, leaving it behind its original position. Now D is going to stay as it is. But then I look to the next particle, this is also going to have to move towards the right side. So what is the part that everyone is going away from? What portion of the sound wave everyone is leaving? So if I look at D, the particle on the left is also leaving. The particle on the right is also leaving. Kind of like sad life, alone time, or lone boy hours, sad boy hours, right? So every particle is leaving this position. So what do we get here? A particle that is going to be under low pressure, right? But very high pressure from life at least, because no one is around. Okay, question number 24. A source emits a sound wave, a single frequency. The Doppler effect causes, okay, Doppler effect, I have to think about this. Okay, frequency sound be heard by the stationary observer. Okay, what is the requirement of Doppler effect to occur? Source that is moving as it produces sound wave. Okay, this is a good answer. A source that produces sound waves do not get polarized, because even if you pass them through a filter, the particles are moving forward and backward, forward and backward, forward and backward. They won't be polarized. They can't be polarized. Incorrect answer. Okay, so sorry, not this one. Source that produces sound wave of changing amplitude. No, that amplitude will only change the loudness, right? D part, a source that produces a sound wave of changing frequency. No, the source has to have a constant frequency, but it has to be moving either towards us or either away from us. So A was the right answer. An electromagnetic wave in free space has a frequency. Okay, fine. I told you, you have to memorize this. There is no other way. You have to memorize the whole spectrum. Please memorize it. This is an infrared wave. I can't help you in this. You have to memorize the whole table. This is calculated as V equals to F lambda. If you want to memorize anything, that's up to you. So 3 into 10 raised to power 8 equals to F is given to you, which is 2.5 into 10 raised to power 14 into lambda. Even if you do find lambda, what are you going to do about it? If you don't remember, if you don't memorize the whole wavelengths or the ranges of wavelengths from gamma to radio waves, you can't solve this question. You can't second guess it. I'm sorry. Now this question requires a bit of, you can say, visualization. So 2 polarizing filters, okay, fine. They sit next to each other. Okay, fine. So the very first encounter is at 50 degrees. How to visualize this? Let's look at it. So this is what a polarization filter will look like. We have a wave that is coming from this side, right, from this side, and it is encountering a filter which is placed at an angle of 50 degrees. So we can see that the wave is actually tilted a bit, or you can see from the very dead straight end, it's actually tilted at an angle of 50 degrees right now, right? So the filter was at an angle of 50 degrees. The wave has, the oscillations have turned 50 degrees in favor of that filter at least. Okay, so if I were to calculate the intensity before and after, let's look at the question first. So it says that we are introducing 8 watts per meter square, right? First, at the very first stage. Let's do that over here. Okay, so what is that? What's happening at this point? So I'm introducing, before the filter, I'm introducing 8 watts per meter square. And after the filter, passing through the 50 degree change, what's the intensity? So the formula goes something like this. So I is equal to I naught cos a square of theta. So this will be 8, because this is what I introduced, into cos square, and the angle is 50 degrees. Now be advised, for God's sake, first take the cos 50, then take the square of the value of the cos 50. Then you will get the answer after the first stage. You will get the answer as 3.3 watts per meter square. So this wave is actually 3.3 watts per meter square of intensity. Okay, first stage is done. Now we move to the second stage. I'm going to clear this out and we move to the second stage. Now in the second stage, he says that it is brought back when the angle becomes 20 and it undergoes a change of 30 degrees. How to understand this? Let's go back to this visualization. Okay, so at this exact moment, I realize that my filter and my wave orientation previously, if this was the plane of vibration of my wave being introduced, now the plane of vibration is this along 50 degrees. This is what we did after passing through the filter, right? That previous wave is actually my introduced wave, and this is now my current wave. He says now we change the filter to have an angle of, let's make an angle of 50 degrees at least. Let's make that this is the plane right now of my wave's oscillation. My wave is oscillating like this now after passing through the first filter. Let's go back to the condition that he gives me, that this is going to go a 30-degree change and go back to the 20 degrees. Now, if I decrease this angle by 20 degrees and go to 20 degrees at this point, just a bit more. Yes. So today, what I've done is I have made this angle between the orientation of my original position, which was at 90 degrees. Now that is 20. But what is the 30 degree as mentioned in the question? That 30 degree is the change that it has undergone from this point. Let me write this with another color. This is that 30 degree change it underwent from the first filter, which was at 50, goes back 30 degrees so that it can have a 20 degree angle from the starting point. Now this is all just to create confusion. We don't care what the orientation is with the original direction. We don't care. It's not our concern. What we care about is what's the angle between the wave orientation currently and the new orientation of the filter. Now the filter is organized along this line. My wave was polarized along this line after passing through the first filter. And when we use the formula I equals to I naught cos square of theta, where is this theta? This theta is between the plane of filter, the current situation, versus the orientation of my wave. Now my wave is actually in the blue direction. My filter is at this direction. What's the angle between them? This is the angle between them, which is 30 degrees. So this is the problem. This is the issue that is difficult to visualize. We don't care about the original direction. What we care about is what is the orientation of the filter today in comparison to what it was received, what it was received by it. So now the equation becomes I equals to I naught cos square of theta. But what did this filter receive? This filter received 3.3 after the first filter. So that becomes the input for the second filter. So this is going to be cos square of 30 degrees. Again, take the 30 degrees first, then take the square, then multiply by 3.3. You will get the answer as 2.5 or 2.47. This is 475 watts per meter square, which becomes 2.5 watts per meter square, which is going to be your option B. Okay. All right. Let me erase this and go back. So this is going to be 2.5. Okay. All right. Question number 27. It says stationary wave. Okay, fine. Which statement about the state is correct? Point R is at a node. No, that is an antinode. Point Q and S vibrate in the phase. Yes, they do. Q will be vibrating downwards, S will be moving downwards, and R will be moving upwards in its next phase of life. So yes, they have the same base. Closest possible option seems to be correct. The distance between P and T is 3 wavelengths. No, wrong. This is the first wavelength and this is the second half of the wavelength. So this is actually 1.5 wavelengths. This is incorrect information. The wave transfers energy. No, a stationary wave does not transfer energy from any point to any point. So the best answer is B. That's why it's called a stationary wave. It does not transfer energy. Now we have a question for simple diffraction. He says that smallest angle of diffraction, which means we want this to spread the least. We don't want this to spread out at all. Now, he has given us the frequency and the gap width. I understand that the gap width has to increase, because if I increase the gap width, then whatever wavefront I receive, they're going to pass without diffraction, with a minimum diffraction actually going to look like this. So I know that I need to increase the gap width. So it should be 2x as opposed to the original. So option A and option C are cancelled. They will not be considered. Okay, so what about the wavelength? For maximum diffraction, I believe that the wavelength and the gap are supposed to be equal at best. Okay, if I want to prevent this, then I can increase the wavelength or I can decrease the wavelength so much so that it doesn't happen. Okay, now if I look at the formula V equals to F lambda, what can we do to the frequency, right? So since lambda is going to be inversely proportional to frequency, I would like to increase the frequency so that wavelength decreases so much so. Why? Because I am increasing the gap width, I'm deliberately making it larger, and I will deliberately make this smaller so that both will have a very large difference between them, because we know that the gap width should be at least greater than or equal to the wavelength for diffraction to occur. Now what we are doing, we are increasing the gap width much more and decreasing the wavelength. We are doing everything in the opposite direction. So the frequency should increase, so I should be choosing not f by 2, but I should be choosing increasing frequency, which is option D. Question number 29, very straightforward. He says where the loudest sound is heard. You see, these are the crest, trough, crest, trough, crest, trough, crest, and trough, so and so, right? Or in terms of a sound wave, this will be compression, rarefaction, compression, rarefaction, compression, rarefaction. Wherever they overlap, wherever the compression overlaps with the next compression, there will be a loud sound or a constructive interference. You see, at this point, this is just a crest alone, encountering a rarefaction, right? The destructive interference. At this point, again, not destructive, but not constructive either. Something in the middle. Okay, so B again is a crest standing alone in its own position, no issues. But if you notice D, this is actually the crest of the first wave, and that is the crest of the second. I keep on saying crest, of course, I mean the compression and the rarefaction in terms of crests and troughs. So when they overlap, I will hear the loudest sound. Let me show you an animation for this. This is how both sources are going to produce a sound. Actually, this is from a light example, but you can see and observe where you can see the loudest pitch or loudest sound, for example. See and observe what's happening at this point. You see, at this location, they're overlapping. At this location, they're overlapping. And when you extend them, you see a bright fringe, bright fringe, a bright fringe. And in the rest of the region, where one is crest and the other is trough, you see a dark fringe. When one is trough, the other is crest, dark fringe, right? I hope you understand this. This is from light, of course. I'm applying the same idea to sound, okay? Question number 30, he says we have an equation lambda d sine theta. Okay, fine. He says what is being represented by everything. So N, no, this was actually D. So N is the intensity of the maxima. Okay, this is the answer. He says D is the distance between adjacent slits in the grating. Yes, that could be the answer. Yes, that is. Distance from grating to the screen, that is not represented in this formula at all. So this is going to be C, most common option, if you know your formula. 31 is again a simple manipulation of algebra. Let's see how it goes. He says that what's the current I in this situation, and some letters and things are given to us. And there's a volume V. And to calculate volume V, I can multiply A, B, and C. If I multiply this, and this, I get the volume. Okay, fine. Each charge carries a negative Q. The number of charge density is N. It takes each charge an average time of T to pass through the block. What's the expression for I? So I is equal to NAQV divided by T. So what's going to be velocity divided by time T? Or what's the distance? If I want to find the velocity in this direction, I should divide B with T. This, no? The distance traveling or distance traveled by the charge, time taken by the charge. He has given me that the time T is going to be taken for this process. So what I can do is I can NAQ and isolate V by T, right? Right. So B by T is actually the velocity. Sorry, this is going to be like this. If I replace B by T, then that is a representative of time T. Oh, sorry, velocity. Okay. All right. Let's look at the cross-sectional area. So cross-sectional area is actually this. Let me erase this to make space for this. So what is a cross-sectional area? Cross-sectional area is this one. So this can be found by multiplying A with C. So AC is cross-sectional area. So let's replace or start replacing everything in this equation. So I is equal to NAQV equals to, N comes as it is, cross-sectional area was A dot C, Q comes as it is, and in place of V, simple terminal velocity, I could replace B divided by T, which was what we found here, is V divided by T will be the velocity. Okay, fine. So in place of V, I can simply write down B by T. So this is B by T. What does this become? This becomes N dot A dot C dot Q dot B divided by T. Now I realize that multiplying A with C with B is actually the volume, right? So this becomes NVQ divided by T, and the most common answer is option B. All right. Okay, so let's move on to the next question. Again, in this question, you are required to invoke the formula P equals to I square R. And then this question would have become very, very easy for you. Power in X, power in Y. Let's calculate that. So P equals to 0.5 square into 9.6. Let's calculate this one. So this will be P equals to 3 square into 1.2. Let's divide them. So X was 0.5 whole square into 9.6 divided by 3 whole square into 1.2. And when you're done calculating this, you're going to get the answer of 0.22, which is option A. Simple. 33 is a part of your memory, should be a part of your memory. He says that the light intensity incident is increased. So the resistance of LDR is inversely proportional to light. If you increase the light, its resistance decreases. The temperature that is increased, again, inverse relation with temperature or heat. If you increase the heat, the resistance decreases. So both of them will experience a decrease in resistance. And of course, if the resistance decreases and the current is constant, by the way, right? So V equals to IR. If you're maintaining a constant value of I and you're decreasing resistances, after multiplying, the value of voltage will start decreasing. So that's why the voltage decreases, or appears to decrease at least. Question number 34. All right, so in this question, he said that the length is 8 meters and the diameter is 0.5. The resistance is standard R. Okay, fine. The second wire has a length of 2 meters. I can see that the length has been decreased by 4. So my resistance, since I know that resistance is proportional to rho L over A, I'm doing a constant proportionality method. So R is proportional to length and R is inversely proportional to cross-sectional area, right? If I reduce length, resistance should also reduce. So if I've reduced the length by 4 times, the resistance should decrease by 4 times. So after compensating for the length factor, my resistance has decreased by 4 times. What should I do with the area? So if I have doubled the diameter, I realize that the cross-section area is pi r square, or diameter d squared divided by 4. Pi and 4 are constant, so area is proportional to d square. If I double the diameter, for example, I make it from 1d to 2d. When I take the square, this becomes 4d square, which means that the area has increased 4 times. If I increase the area by 4 times, the resistance decreases by 4 times. So there is another factor of 1 by 4 involved in this. So the resistance has decreased 16 times from the standard value of R, which we started with. So this is going to be option A. Question number 35 is a definition. It says that it's an EMF, okay, connected fixed resistor. Over time, the internal resistance of the cell increases. And we know that if, let's say, we have a cell with an internal resistance and an external resistance, he says this is R, this is capital R, this is EMF, and the formula becomes E equals to IR plus IR. Let's say this is the current I in the circuit. He says that the internal resistance is increasing. If this is increasing, then the share of the external resistor will start decreasing because the EMF can only do so much. What changes occur in the internal resistor of the cell occur as the internal resistance of the cell increases? Okay, a decrease in the charge, no. A decrease in the potential difference measured across the cell, yes. When internal resistance increases, lost volt increases, and if the lost volts are increasing, you will get less and less voltage with the passage of time. An increase in the energy dissipated per unit time, no, it will not be possible because you're getting less voltage, so the energy dissipated will be lower than before because power is also equal to V squared by power. You're getting lesser voltage, you're getting lesser power. An increase in the number, no, charge carriers do not depend on this. Charge carried depend on the volume or depend on the material itself. Number of electrons per unit volume. So the B was the closest answer. 36, Kirchhoff's the second law. First law is about charge and current, and the second law is about energy and no other option. So option A seems to be the best answer, but this would have been a second choice if charge was not given. Charge is the first choice, energy is the first choice for the second law. 37 is tricky. What he has done, he has given you option A as the incorrect answer, which is the most common answer, the common technique that we as teachers teach in the classroom. So what he did, he actually gave you this example as the most familiar one. This would have been correct or acceptable if the polarity of this cell would have been exactly the same as the E0. You say E0 is the cell that is known. We know the position of E0, and for the null method that we're using right now to find this EMF of the unknown cell, we know that the known cell should have a higher voltage, okay, and that its voltage is dispersed along the line, a length of another wire, okay. So this should have also been positive and this should have been negative. So both of them can actually have a fight or can actually have a tussle at this point. So this was why this option is incorrect. And this is why everyone selected option A, because it looked familiar. They didn't pay attention to the cell's dimension. Option B is wrong. It is wrong. Why? Because E0 is supposed to be connected over here and EX is supposed to be compared with this wired junction method. C was incorrect because ammeter has to be connected over here, although their terminals were correct. D is the right answer. If you notice that this is the plus sign, this is plus sign, both will have a positive voltage at this location. And of course, ammeter connected with the unknown cell and E0 being its voltage dispersed along the wire because it has a higher voltage. It is the cell which is being compared for the voltage of EX. Question number 38. In an experiment, alpha particle scattering, again, alpha based on memory, he says gold foil, we know what happened, we know everything. Which statement cannot be deduced from this experiment? What we cannot say about the experiment from this? Atoms are mostly, we know that, 99% empty space. Why? Because everyone passed straight through. So we deduce that they are mostly empty. Most of the mass of the atom, yes, because the alpha particle that came right in front of it actually got deflected back. So it means that this is a very, very massive object which is not letting anything pass by. The nucleus of an atom, no, this is what we don't know yet. The nucleus of an atom compares small, yes, because 99% of them passed straight through. So it's very small. Now, the nucleus where protons, we didn't know that because the nucleus appeared to be positively charged from the outside because alpha was approaching it and changing its direction because alpha was also positive. We did not know what was inside it at that time when we conducted the experiment. It was later found out by hadron colliders that nucleus has protons and neutrons, right? So this is what we did not know at that point. 39. You just have to test out all the options, okay? And to test out all the options, you will see that option A says that an uncharged atom of Q has 24 orbital electrons. No, it would have 13 electrons because protons are equal to neutrons. Protons are equals to number of electrons. So nucleus G and M are isotopes of the same element. M and G, they should have had the same protons. This is 12 is not equal to 15 of the G. When M emits a beta particle, let's consider this M. We have M25 with 12 emits a beta negative. What is being formed transforms into Q. So Q is 24, 30. No, this looks right, but this is wrong. Option C is the right answer. You can try this by charge conservation method and decay equation. So we understand what are up and down quarks. A neutron decays to proton. We understand that. What is the quark composition? So a neutron disintegrates to become a proton and a beta particle, which is 0 - 1 plus with an antineutrino. Okay. So option A and C will be rejected because they don't have an antineutrino. Now let's move to the quark composition. So this is up, down, down. This is up, up, and then down. Now this is your job to memorize this. And we know that up has a charge of plus 2 by 3e. This is minus 1 by 3e. This is minus 1 by 3e. Overall charge 0. This is plus 2 by 3e. This is plus 2 by 3e. This is minus 1 by 3e. Overall charge plus 1. This overall charge becomes minus 1e at least. So the closest option was that a down actually changes to an up. If you observe this, a down has changed into an up. So a down changes to up, releasing a beta negative and an antineutrino. B was the correct answer.